Okay, this is section 2.1, the start of chapter 2, obviously, and the title is Using Variables. To jump right in, a variable, a word you've probably heard of before, probably not a new thing. A variable is a symbol that represents one or more numbers. Usually by symbol we just mean a letter of the English alphabet. Like X is maybe the most common one by far, actually. But it doesn't have to be a letter in the English alphabet. It could be a Greek alphabet letter or a letter from the Greek alphabet. But don't want to go too far down that rabbit hole or down that path. So symbol really just means a letter that represents one or more numbers. Remember, sometimes a variable, there's literally only one number that variable could be, like in disguise. Or sometimes a variable we put in a spot where it could be like an open-ended thing. Like it could be like almost maybe any number you want. But it represents sometimes only one number, sometimes more numbers, sometimes two numbers, sometimes all numbers, any number. And then an algebraic expression is just a math phrase that includes numbers, variables, and or operation symbols. Okay? And again, as always, you can pause if I'm moving ahead to the next page all too fast for you. So write an algebraic expression for each phrase. You must define a variable if necessary. So like down in number 5, for example, they actually say like t, and here they say y, but in others of these, in other ones, they just say a number, and so you get to pick your own variable. But number 1, for this phrase, what would be the math expression or the algebraic expression? How do you write 3 more than x in math? Like that, with addition. If you do x plus 3, that's 3 more than x. Like this represents a quantity that's 3 more than whatever x is. It's 3 higher than whatever x is. Number 2, the product of 7 and some number. I wonder what I'm calling a number. Maybe x, maybe n. I don't know. But the product means we're multiplying it. So it's 7 times some number, which I'm calling x. N minus 6. Well, that kind of just as it's read. And then 9 less than 2 times a number. So how do we write that? Well, first of all, 2 times a number, I'll just use x again. And then how do you represent something that's 9 less than that? Think about it. Just some random number like 50. What's 9 less than 50? You're probably thinking, well, 41. 41 is 9 less than 50. Now think about it. Did you do 50 minus 9, or did you do 9 minus 50? Let me say that again. 9 less than 50. Do you do 9 minus 50 to get that? Or do you do 50 minus 9? Well, you do 50 minus 9. So when you say, and remember, subtraction is not commutative. So writing this as 9 minus 2x is wrong. Number 5, the difference of t and 8. Difference means subtraction, so that's the math expression. The quotient of 12 and the sum of y and 5. So I can see where there's a lot here, and the water is a little bit muddy with like all of this going on, but read this again. The quotient of 12 and the sum of y plus 5. So it's a quotient of 12 and this sum. So overall it's a quotient, okay? So you're basically adding those together, because that's what sum means, and then it's the quotient of 12 and that. So you could write it like that, or let's see, because my board is not on, so let's change to that. Okay, so this is correct, or this is also correct because you're dividing, but look, I'm going to put y plus 5, this sum, in parentheses, because you'd have to kind of get that first, and then it's the sum of 12, or the quotient of 12 and whatever this is. So a couple different ways to write that. All right. Moving on. An equation is a mathematical sentence that uses an equal sign, of course. So I guess to elaborate on that, an equation is like an expression, I guess, like some kind of math sentence, some kind of math, thing. You're writing out some math, but if there's no equal sign, okay, there's no equal sign, you're probably just looking at an expression. But with an equal sign, now you're probably talking about an equation. So that's all this is about, kind of separating this from just an expression. Now it's going to be an equation because it's got an equal sign. All right, so look at this. Suppose the manager at Best Buy raises the price of CDs to $15. Now, even in 2024, if you're watching it in 2024, I'm going, CDs, holy crap, do they even sell CDs anymore at Best Buy? Probably not, actually. But suppose the manager at Best Buy raises the price of CDs to $15. Write an equation for the cost of n CDs. Then complete the table. So, then complete the table. I suppose you can do it in the other way, like you could complete the table, then write an equation that represents the cost of n CDs. So if you're buying one CD, well, wouldn't that be $15? I guess we're not really factoring in tax here. Oh well. Speaking of muddying the water, let's not muddy the water talking about tax. Let's just assume that one CD would just cost you $15, 2 CDs would cost you $30, 3 CDs, well, if each of them costs $15, again, hopefully you're picking up the vibe of, multiplication, right? Okay, we're skipping 4. How about 5 CDs? If each one of them costs $15, that's $75 total. And then for 10 CDs, $15 each, that's $150. So what would be an equation that, like, how about for n CDs? So, I mean, something maybe to say or reveal right away is there's going to be another variable in this equation. We're going to say C represents the cost. So the cost of your purchase will equal what? If you're having like n CDs. If n, like, treat n as a number. If n is the amount of CDs you're buying, then what's going to be the total cost of all the CDs. If there's n, excuse me, if there's n of them. Well, oh my gosh, really? Well, it's going to be something times n, okay? So maybe I'll drag this out a little bit more then. So if there was 5 CDs, like if that's the number of CDs, what do? You just multiply it by 15, and that's what got this. If there was 10 CDs, what do? You're multiplying it by 15 to get the total cost. Well, if there's n CDs, you're just going to do the same thing, multiply by 15. So this is the equation. The cost, your total cost, is going to equal 15 times the number of CDs that you're buying. There you go. Next example, the total charge is the number of miles times basically 21 cents, or maybe I should say $0.21, combined with $145 insurance. So I guess there's like this one-time cost of $145 for the insurance. Like, let's say you're renting a car, from, my gosh, I can't even think of a car rental company right now. This is crazy. Well, maybe not too crazy considering I've just about never actually rented a car in my life. That's not true, but close enough to being true. Oh my gosh. Oh, what's the yellow one? Hertz? Probably. So let's say Hertz is an actual. So you're renting a car from Hertz, and $145 for the insurance, but then you're gonna have to pay $0.21 for every mile. Okay, and so here we go. It doesn't really say this, but the directions here. Trust me, you're supposed to write an equation that represents like the total charge for any number of miles. Let's say for m miles, or we could just as quickly or just as easily choose x for the number of miles. But I'm going to assume that we're going to use m for the number of miles. So m is the number of miles, and I don't know, maybe t, maybe c. I guess we'll see for the total charge. And we're going to have to write an equation. Well, yeah, it looks like t. So the total charge is going to be what? Based on m total miles. What do you think? Oh, of course. Well, so what happens is whatever the number of miles is, whether it's 50 miles or 125 miles or 1,000 miles, whatever that is, again, it's m in the equation, it's open-ended. Whatever that number of miles is going to get multiplied by 0.21, but then we have to add that one time 145 for the grand total, and that's what's going to equal t. Okay. A few more examples. Write an equation for the data in the table. So let's see. If we have a $20 purchase, $19 purchase. So this is a table that kind of describes the relationship between the cost of whatever you're buying with the change you would get if you were paying with a $20 bill. So if your purchase costs $20, you're going to get no change. If you spend $19 and you pay with a 20, you're going to get $1 back. So, I mean, can you think of an equation that represents or compares? Now look, this is almost like a side lesson, but this second column is what you like. If see again, it's almost like a side lesson where I could start going into independent variables, and dependent variables, domain and range, input and output. So your first column is generally your input or your x, and the second column is generally your y. So in an equation, do you usually have like x equals blah 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 with a y, or do you normally have y equals blah blah blah? It's the y. Okay, so anyway, what am I really getting at here? This is going to be on the left side. So it looks like I'm using C for the change. Okay, so I'm calling the change from a 20 C. So what would be it? So what would this be? I'm gambling here. P. Okay, so it looks like I'm calling the purchase price, or the price, P. So what would be like the change? How do you calculate the change? Wouldn't the change always be the $20 minus your purchase? I mean, whatever your purchase is, you know, whether it's 20 minus 20 or 20 minus 19, because here P is 19, or 20 minus $17.50. So that equation makes sense. All right, moving on. Next example. Let's keep this going. Let's keep it moving. Amount earned. I'm gonna go out on a limb and say in the equation we're gonna call that E, and make sure this doesn't look like a 5, which it could be better. I like writing with a mouse. Looks like a snake, so I guess it's fine. All right, so amount earned and amount saved. This is an interesting relationship of variables. The amount earned and then the amount saved. Okay, well, the bottom line is we're going to have this is going to be like the S equals, because it's the second column. All right, so what's going on here with amount saved versus amount earned? It appears, I'm not going to bet my life on it just yet, but it appears that the amount saved is always going to be half of what you earned. It looks like we're able to save about half. I mean, right? 840. Actually, wait a second. What is going on? Is this a mistake? What the heck? So 1159. I don't like this. Like, was it? Which one was supposed to be? Was this one supposed to be correct? Probably not. What is going on here? Did I fix this in the for your notes? So what is this? 2.1. What the heck? It's not good. Yeah, this was something's going on there. My mistake. Which that'll have to be fixed, won't it? But there you go. The savings will always equal E divided by 2. Last example, U-Haul charges a flat rate of $25 to rent a moving truck. Upon return, you must pay 40 cents for every mile you drove. This sounds like this one where I said maybe it's Hertz. You're renting a car. Well, here you're renting a U-Haul, a big truck. So it's kind of similar. Ooh, again, disregard refilling the gas tank, which that's, again, not to get distracted here by unimportant details, but in real life, you also normally have to like refill the gas tank too, or you also have to pay for your gas. So, but here, let's not worry about that. Flat rate of $25. Okay, plus 40 cents for every mile you drove. Write an equation for total cost. So I don't know if I called this T or C. What would be the other variable again? Like, what's the other thing that varies, or what does the total cost depend on? What's the other open-ended unknown quantity that varies, that could vary, and that's why they're called variables. But what else is going to get a variable? Well, wouldn't it be the number of miles? Yes, it would. So, oh, you see, I should have known. And so there you go. It's going to be 0.4 times m, which is like 40 cents. 40 cents times whatever the number of miles is, plus this $25. But then again, in real life, also plus the gas that you used, you know. Okay. Thank you for following along. That was 2.1.